Hey guys, in this video we're going to be talking about the last concept that Chapter 5 covers, which is actually falling and air resistance. It's 5.7 if you see, and I believe it is the last subchapter. Yes, it is. So basically what we're going to talk about when we talk, normally in physics in this class, we've always kind of disregarded air resistance. We've always said, okay, air resistance is negligible, don't include air resistance, but in reality, air resistance is very predominant and very present. So we're going to talk about it a little bit now. You guys know what free fall is, and free fall is the absence, right? Free fall, whoops, free fall, falling, falling without air resistance, okay? But now we're going to talk about falling with air resistance, okay? So you guys may have heard the term terminal velocity or terminal speed, terminal S or V, okay? Terminal velocity or speed. But before I give you a quick definition of it, I'm going to kind of dissect the word. So terminal, that word itself, term, okay, mainly the prefix term there, means end, okay? End or final, right? So just based on that, what do we think this is going to mean? End speed. End speed or final speed, something of that nature, right? So when we talk about terminal velocity, we're going to look at projectiles or particles that are falling, or just objects falling down. So this boulder is falling downward, okay? I like to use the boulder example, right? And so in free fall, we'd say, okay, it's just going to fall straight down at 10 meters per second acceleration because there's no air resistance. But really, there is air resistance. So what's going to happen? If it's falling from an airplane, okay, it's eventually going to hit a point, maybe right here, where it stops accelerating, where its acceleration is 0 meters per second squared. Of course, it's still going to have a velocity. It's still going to be moving, maybe 500 kilometers per hour. That could be its velocity, which would be pretty fast, but at one point in its fall, it's going to stop accelerating. It's going to stop changing this number. So yeah, so remember, acceleration is the change, so it's the change, delta change in velocity, okay? So at one point here, it's going to stop accelerating. And that is what defines terminal velocity. When something reaches the point where it no longer, when something falling reaches a point where it no longer accelerates, it has reached its terminal velocity. So when do you know that something's reached its terminal velocity? Well, it's pretty simple. Let's say this boulder weighs 50 newtons, okay? 50 newtons. And remember, newtons is a unit for force and weight because weight is a force. It's a pull by gravity. So 50 newtons. I'm sorry for my bad penmanship. I'm still getting used to writing with the pen on the computer. But when this, so let's say right now there's a little bit of air resistance, yeah, here's the air. I mean, the air resistance is always going to be the same, but it's always adding a force on this ball, okay? Obviously you wouldn't really see these blue streaks. This is kind of the air. But it's hitting these blue streaks constantly, and that takes a force to overcome. So each of these little blue streaks, I mean, technically it's the air molecules, oxygen and whatnot, in our atmosphere are causing resistance on this falling boulder. So at some point, it's going to reach a point where, or maybe down here, after a couple seconds later, it's going to reach a point with which the force of the sky, also equals 50 newtons. I shouldn't use sky. The force of the air resistance force, air resistance force. You can think of it as a push. Remember, we defined force as push, pull. Think of it as a push here. So once the air resistance equals 50 newtons, it is the same as the weight of the boulder. That's when you're in terminal velocity. You're not going to accelerate anymore. That's when the 0 meters per second squared acceleration comes in. So you're no longer going to accelerate. Now another thing to talk about when you're talking about terminal speed is, well, how do I reach it? How do I reach it quicker? Sorry about that. Quicker, faster. Well, it has a lot to do with surface area. Okay, so if you ever seen like flying squirrels, they kind of have those wings, and parachutes are a great example, or skydivers with the wings and whatnot. So the larger surface area, the largest area, the larger the area you have touching the air, the more air resistance there's going to be. So let's say you have this big, like, kind of big, like, cloth sheet. It's not the best drawing of a cloth sheet, but it's kind of falling from the sky, okay? And it has a lot of surface area, a lot of area. Big A, okay? But then you also, let's say you have this rock, okay? It's very, very small. Small pebble has a small a. The air resistance over here, air resistance, is greater. And then less AR, or abbreviation there. Less AR. So intuitively, what do you think is going to happen? This object is going to reach its terminal velocity much faster. So, because since the air resistance is so much larger, the force opposing it by the air is going to get larger and larger, faster and faster, because it has a larger area. So that's just how that works. And then you could then take into account the weight of each object. So of course, if the pebble weighed like 1,000 newtons and the sheet 5, then yes, the same thing would happen. But the key factor here is the surface area. Is how is it going to catch more air, catching more air. And then so yeah, that's something to think about. You have to take into both the weight or force in newtons, the force of gravity acting on it, and the surface area when you're trying to find how fast something will reach its terminal velocity. A very strange case would be if you had, well, not very strange, but if you had something, with a large surface area and then a very large weight as well, so like 1,000 newtons, because then it's going to reach it, since the surface area is so big, the air resistance is going to get larger and larger, but it's going to take a much longer time to reach 1,000 newtons to get to equilibrium, to get to terminal velocity. So that's kind of an interesting nuance. But yeah, that's about it for terminal velocity. I suggest that was kind of a quicker explanation, but definitely go through the chapter as well, maybe while you're watching the video, so I can act as kind of an auxiliary teaching lesson. So one last thing I want to talk about. I hope you guys will stay on and listen to this for the last couple minutes. Although this may not apply to you. If you think these videos are helpful, then that's great. I know I've had a couple students already benefit from it, which I love. That's why I'm doing it. So it just gives me more motivation to keep doing it. But I did want to talk about how, since I'm having so much fun, I think I'm going to branch out to some other subjects that I enjoy. So I know that Algebra 2 is supposed to be difficult for a lot of students. It's kind of a precursor to pre-calculus, which is a tough subject. It's just kind of, Algebra 2 is a big jump up from Algebra 1. So I will be offering Algebra 1 and Algebra 2 videos. Algebra 1 and 2 videos, starting probably right after I make this video, So I love both of these subjects, and I'll probably start off with Algebra 1, the basics. I have all the books that Prairie uses, and I know the teachers well, and I like the teachers, so definitely stay tuned for those as well, because I hope that this little YouTube channel can branch out as far as possible and benefit as many people as possible. So I'll see you guys in the next video, math or physics.